Welcome to this walkthrough of problem number 1001, Grid Illumination. In this session, we'll explore the problem, break it down step by step, and discuss strategies to solve it efficiently. Let's dive in and illuminate the grid together. In this problem, we are working with a grid of size nxn, where each cell can potentially be illuminated by a lamp. The goal is to determine whether specific cells in this grid are illuminated and to handle the turning off of lamps as we process queries. Each lamp placed on the grid illuminates the entire row and column it is in, as well as the two diagonals that intersect its position. This means that the light from a single lamp can affect multiple cells at once. You are given a list of lamp positions, and for each lamp, its position is defined by a pair of coordinates, row, col. Additionally, you are provided with a list of queries. For each query, you need to determine if the cell at the specified coordinates is illuminated. If the cell is illuminated, you return 1, otherwise, you return 0. Once a query is processed, the lamp at the queried cell, along with any lamps in the 8 surrounding cells, must be turned off. The grid size n can be very large, so efficiency will play a critical role in solving this problem. The queries list contains multiple pairs of coordinates, where each pair represents a cell on the grid that we need to check for illumination. For every query, if the cell is illuminated, we return 1, otherwise, we return 0. The output of the function is a list of integers, with one result for each query in the order given. To illustrate how this works, consider an example. Suppose the grid is of size 5x5, with two lamps placed at positions 0, 0, and 4, 4. Now, we have a set of queries to process 1, 1, 1, 0, 0, 2, 4, 4, and 3, 3. The goal is to determine whether each of these cells is illuminated, return the corresponding results, and turn off any affected lamps as we process each query. This ensures that the illumination status changes dynamically as the queries are resolved. For the first query, 1, 1, we see that this cell is illuminated because it lies on the diagonal of the lamp at 0, 0. Therefore, the result for this query is 1. After processing, the lamp at 0, 0, and its neighboring cells are turned off. The second query, 1, 0, checks a cell that is no longer illuminated, so the result is 0. Next, the query, 0, 2, targets a cell that is illuminated because it shares the same row as the lamp at 4, 4. The result here is 1. Then, for the query 4, 4, the cell is directly illuminated as it contains a lamp. The result is 1, and the lamp at 4, 4, and its neighbors are turned off. Finally, for the query 3, 3, the cell is no longer illuminated, so the result is 0. This example demonstrates how the illumination of cells changes dynamically as lamps are turned off during the query process. In another example, consider a smaller grid of size 3x3, with lamps placed at 0, 1, and 2, 2. The queries to process are 0, 0, 2, 2, and 2, 1. For the first query, 0, 0, the cell is illuminated because it is in the same column as the lamp at 0, 1. The result is 1, and the lamp at 0, 1, and its neighboring cells are turned off. Next, the query 2, 2, targets a cell that is illuminated because it contains a lamp. The result is 1, and the lamp at 2, 2, and its neighbors are turned off. Finally, the query 2, 1, checks a cell that is no longer illuminated, so the result is 0. This problem includes constraints such as handling up to 20,000 lamps in queries efficiently, processing overlapping lamps correctly, and ensuring repeated queries don't cause errors. By addressing edge cases like an empty lamps list or large input sizes, we ensure robustness in the solution. The dynamic nature of turning off lamps as queries are processed adds an additional layer of complexity to the problem, making it an interesting challenge to solve. To solve the grid illumination problem, let's start by understanding the brute force approach. The intuition here is to simulate the problem directly by checking whether each query cell is illuminated. A lamp illuminates all cells in its row, column, and both diagonals. For every query, we would traverse the grid to determine if the queried cell falls within the illumination range of any active lamp. After processing the query, we would turn off any lamps within the 3x3 region surrounding the queried cell. However, this approach is computationally expensive. If there are m queries in k lamps, processing each query takes O, k, steps, and checking illumination across the grid adds an n squared factor. For large grids, this quickly becomes infeasible. To address this, we can consider an optimized approach using hash maps. Instead of directly simulating the illumination across the grid, we pre-compute and track the illumination state using hash maps. These hash maps store counts of how many lamps illuminate each row, column, and diagonal. Using this data structure, we can efficiently check if a query cell is illuminated, and when a lamp is turned off, we simply decrement its contribution in the hash maps. This avoids the inefficiencies of the brute force method while maintaining accuracy. There are key observations that help us refine this approach further. First, a single lamp illuminates its entire row, column, and two diagonals, the primary diagonal, where the difference between row and column remains constant, and the secondary diagonal, where the sum of row and column remains constant. By tracking only these four dimensions, rows, columns, and the two diagonals, we avoid simulating the entire grid. This significantly reduces the computational overhead. When a lamp is turned off, we simply decrement its contribution in the hash maps for its row, column, and diagonals. This ensures we can efficiently update the illumination state without needing to revisit the grid. The complexity of this optimized method is worth noting. Pre-computing the initial illumination counts 4K lamps takes K time. Then, each query is processed in constant time, 1, for both checking illumination and turning off lamps. As a result, the total complexity for M queries is K plus M. This makes the approach highly efficient for large values of N, K, and M, where the brute force approach would have struggled. Given these considerations, the optimized approach using hash maps is the clear choice for this problem. It provides a scalable solution that efficiently handles large grids with many lamps and queries. While the brute force approach is conceptually simple and straightforward to implement, its computational cost makes it impractical for larger inputs. On the other hand, the hash map solution introduces a slight increase in implementation complexity but offers substantial performance benefits. This trade-off is well worth it, as the hash maps allow us to eliminate unnecessary computations and focus only on relevant illumination counts. This approach was chosen because it strikes an ideal balance between clarity and efficiency. It leverages the structure of the problem to minimize overhead, ensuring that we can handle scenarios with large values of N, K, and M effectively. By optimizing for both time complexity and scalability, this method ensures that the solution remains robust even for the most challenging test cases. In this problem, we are working with an NXN grid where some cells contain lamps. Each lamp illuminates its entire row, column, and both diagonals. The task is to process a series of queries to determine if specific cells are illuminated before turning off any lamps in the queried cell and its surrounding 3x3 region. The challenge lies in efficiently tracking the illumination status as lamps are added or removed. To approach this, we first observe that a lamp affects four specific directions: horizontally across its row, vertically along its column, and along the two diagonals. This means we need a way to dynamically track these illumination patterns. A brute force approach, where we check every lamp for every query, would be computationally expensive, especially for large grids, so we need an optimized solution to handle this task efficiently. To implement an efficient solution, we use specific data structures. First, dictionaries are used to track the number of lamps illuminating each row, column, and diagonal: row_count 4 rows, col_count 4 columns, diagram 1_count 4 diagonals with a positive slope, and diagram 2_count 4 diagonals with a negative slope. Additionally, we maintain a set called lamp_set to store the active positions of lamps for quick lookup and removal. Initialization involves parsing the list of lamp positions and populating these data structures. When processing a query for a cell at position C, we check if it is illuminated by verifying whether its row, column, or either diagonal has active lamps. If the cell is illuminated, we record the result. Then, we deactivate lamps in the 3x3 region centered around the queried cell, updating the dictionaries and removing the lamps from the set. Finally, we return the results for all queries. Several key insights make this algorithm efficient. First, diagonals can be uniquely identified using the differences row call for positive slope diagonals and row plus call for negative slope diagonals. This allows us to track diagonal illumination without explicitly iterating over every cell. Second, by using a lamp_set, we ensure that we only deactivate lamps that are currently active, avoiding unnecessary operations. These optimizations enable us to determine whether a cell is illuminated in constant time using the dictionaries. Handling edge cases is also important. For instance, we assume valid input, so queries outside the grid bounds do not occur. For overlapping queries, we ensure proper handling of lamp deactivation to maintain accuracy. The algorithm is designed to scale efficiently, even for large grids with dimensions up to 10,000. The time complexity analysis highlights the efficiency of this approach. Initializing the data structures requires O(k) time, where k is the number of lamps, as we iterate through the lamp list once. Query processing is O(m), where m is the number of queries, because each query involves constant time checks using the dictionaries. Lamp deactivation is also O(1) per query, as it is limited to a fixed 3x3 region around the queried cell. Overall, the algorithm operates in O(k) plus m time, making it scalable for large inputs. To implement the solution, we first initialize the dictionaries and the lamp_set with the initial lamp positions. For each query, we check if the cell is illuminated using the dictionaries, record the result, and then deactivate lamps in the surrounding region, updating the data structures as needed. The pseudocode provides a step-by-step outline of these operations. The pseudocode continues with processing queries. For each query, we determine if the cell is illuminated by checking the counts in row_count, col_count, diagram1_count, and diagram2_count. If any of these counts is greater than 0, the cell is illuminated, and we append 1 to the results list, otherwise, we append 0. Next, we deactivate any lamps in the 3x3 region centered around the queried cell by removing the lamp from the lamp_set and decrementing the corresponding counts in the dictionaries. Once all queries are processed, the results list is returned. As an example, for a 5x5 grid with initial lamps at 0, 0, and 1, 0, and queries at 1, 1, and 1, 0, the output would be 1, 1, indicating that both queried cells were illuminated before processing. This demonstrates the algorithm's ability to efficiently handle illumination checks and lamp deactivation. Here, we begin by importing the default dict class from the collections module, which allows us to automatically initialize dictionary values. Inside the solution class, we define the grid illumination method, which takes the size of the grid n, an array of lamp positions, and a list of queries. We initialize 4 dictionaries: row, col, diagram1, and diagram2. These track how many lamps are illuminating each row, column, and diagonal. Additionally, we create a lamp_position set to store the active lamp coordinates, ensuring that no duplicate lamps are added. Next, we iterate over the lamp's input. If a lamp's position is not already in lamp_positions, we add it and increment the corresponding counts in the row, col, diagram1, and diagram2 dictionaries. This ensures that each lamp updates the illumination status of the cells it affects. We also define a helper function turn_off to deactivate a lamp. If the given coordinates are in lamp_positions, this function removes the lamp and decrements the illumination counts for the affected row, column, and diagonals. Finally, we initialize an empty list, result, which will store the output for each query. Now, we process the queries. For each query at coordinates x, y, we first check if the queried cell is illuminated. This is done by verifying whether the corresponding row, column, or diagonal dictionaries have a count greater than 0. If the cell is illuminated, we append 1 to the result list, otherwise, we append 0. After determining the illumination status of the queried cell, we turn off any lamps in the surrounding 3x3 grid. This is done by iterating through all possible relative offsets dx and dy in the range of -1 to 1. For each offset, we calculate the new coordinates, nx, New York. If these coordinates are within the grid boundaries, we call the turn_off function to deactivate the lamp and update the illumination counts accordingly. Once all queries are processed, the method returns the result list containing the illumination status for each query. Here, we start by defining the main structure of the solution. First, we import the necessary Java utilities and define the solution class. The grid illumination method takes the grid size n, the positions of the lamps, and the queries as input. To manage and track illumination, we use 4 hash maps: row, col, diagram 1, and diagram 2. These maps maintain the count of active lamps illuminating each row, column, and diagonal. Additionally, we use a hash set called lamp positions to store unique lamp positions, encoded as a single long value to handle their 2D coordinates efficiently. This ensures that duplicate lamps are ignored. Then, we iterate over the input lamp positions, initializing their counts in the respective maps. For each lamp, we increment the illumination count for its row, column, and the 2 diagonals it's on. The use of these data structures allows us to efficiently track and update illumination as we proceed. The next step is to process the queries. First, we define an array to store the results, where each element corresponds to whether the queried cell is illuminated or not. We also define a directions array to represent the 3x3 grid surrounding any given cell, including the cell itself. For each query, we check if the queried cell is illuminated by examining the counts in the row, column, and diagonals using the hash maps. If any of these counts are greater than 0, the cell is illuminated, and we set the result to 1, otherwise, it's 0. After determining the illumination status of the cell, we proceed to turn off any lamps in the 3x3 grid around the queried cell. For each position in this grid, we compute its coordinates and encoded position. If the position is valid and contains an active lamp, we remove it from the lamp position set and decrement the corresponding counts in the row, column, and diagonals, ensuring to remove any entries that reach 0. This ensures that illumination is updated accurately as lamps are turned off. Finally, we complete the process of turning off the lamps by continuing to decrement the counts for the diagonals, diagram 1 and diagram 2, in addition to the row and column. If the count for any diagonal reaches 0, we remove it from the respective hash map to keep our data structures clean and efficient. By iterating through all the queries and updating the illumination status dynamically, we ensure that the solution handles each query correctly. At the end of the method, the result array, which contains the illumination status for each query, is returned as the output. This implementation makes use of hash maps and a hash set to efficiently manage the state of the grid and the lamps, ensuring that the solution operates within the constraints of time and space complexity for large inputs. This concludes the Java implementation of the grid illumination problem. Here, we are starting with example 1, which is a basic case to demonstrate the solution. The grid size is 5 × 5, with 2 lamps placed at positions 0, 0, and 4, 4. The queries we need to process are 1, 1, and 1, 0. To begin, we initialize the data structures to track the state of illumination. These include dictionaries for rows, columns, and the 2 diagonals, as well as a set to store the positions of the lamps. When adding the lamps, we first consider the lamp at 0, 0. This updates the row, column, and both diagonals associated with that position. The same process applies to the lamp at 4, 4, updating its respective row, column, and diagonals, while also accounting for overlaps in the diagonal values. These updates allow us to keep track of how each lamp contributes to the illumination of the grid. After adding the lamps, the state of our data structures is as follows: rows 0 and 4 each have 1 lamp, columns 0 and 4 are illuminated, and the diagonal values reflect the overlapping illumination where applicable. We then process the first query, which is 1, 1. To determine if the cell is illuminated, we check the row, column, and diagonals for non-zero values. Here, the diagonal diagram 1 has a value of 2, indicating that the cell is illuminated. We append 1 to the result. Next, we attempt to turn off any lamps in the 3x3 grid centered around the queried cell. However, no lamps are found in this area, so the state of our data structures remains unchanged. At this point, the result list contains a single value, 1. Now, we process the next query, which is 1, 0. Again, we check the row, column, and diagonals to determine if the cell is illuminated. The column value col, 0, is non-zero, meaning the cell is illuminated. We append 1 to the result. Following this, we turn off any lamps in the 3x3 grid around the queried cell. This time, we find and turn off the lamp at position 0, 0. Turning off this lamp means we need to decrement its contributions to the row, column, and diagonals. After this update, row 0 and column 0 are no longer illuminated, and the diagonal values are adjusted accordingly. The result list now contains 1, 1, which represents the illumination status for both queries. Let's now look at example 2, which involves an edge case with overlapping illumination. In this case, the grid size is 3 times 3, and we have 3 lamps placed at positions 0, 0, 0, 1, and 1, 0. The queries to process are 1, 1, 0, 2, and 2, 2. We start by initializing the data structures just as we did before. When adding the lamps, the first lamp at 0, 0 updates its corresponding row, column, and diagonals. The second lamp at 0, 1 adds additional contributions to row 0 and column 1, as well as impacting the diagonals. Similarly, the lamp at 1, 0 updates row 1, column 0, and the diagonals. After adding all the lamps, we observe overlapping illumination in row 0, column 0, and the main diagonal, which is reflected in the state of the data structures. To address the first query 1, 1, we check the illumination status by examining the row, column, and diagonals. Since the cell is illuminated, we append 1 to the result. We then turn off all lamps in the 3x3 grid around this cell, which includes the lamps at 0, 0, 0, 1, and 1, 0. This effectively removes all active lamps, resetting the rows, columns, and diagonals. Next, we process the remaining queries 0, 2, and 2, 2, following the same procedure, checking illumination, appending the result, and turning off any nearby lamps. Ultimately, the output for this example is 1, 1, indicating that both queries were illuminated at the time they were processed. In analyzing the time complexity, we start with the initialization of lamp positions. Here, we iterate through the list of lamps, which gives us an O, L, time complexity since there are L lamps. For each lamp, we add its position to a set and update the illumination counts for rows, columns, and diagonals using dictionaries. These operations are constant time, O1, for each lamp. Therefore, the total time for initialization remains OL. Next, we consider the process of handling the queries. For each query, we determine if a cell is illuminated by performing dictionary lookups for its row, column, and diagonals. Each lookup is O1. Additionally, we turn off any lamps in the surrounding 3x3 grid. This involves iterating over up to 9 cells and performing constant time operations like checking, removing lamps from the set, and updating illumination counters. Since these steps are bounded by the number of queries Q, the total time for processing queries is OQ. Together, these two steps result in an O, L plus Q, time complexity for the entire solution. When we combine the time complexities of initialization and query processing, we see that the overall time complexity is O, L plus Q. Now, moving on to space complexity, we start by examining the lamp_position set, which stores all unique lamp positions. In the worst case, this requires O, L, space, where L is the total number of lamps. Then, we have the illumination counters stored in the row, call, diagram 1, and diagram 2 dictionaries. The row and call dictionaries can each hold up to n keys, one for every row and column in the grid, while the diagram 1 and diagram 2 dictionaries, which track diagonals, can together store at most 2 and 1 keys due to the grid's dimensions. This means the total space required for these dictionaries is O, n. Finally, the result array, which stores the output for each query, has a size of O, q. Adding these components together, the total space complexity of the solution is O, L plus n plus q. To better understand the algorithm's performance, let's analyze it under different scenarios. In the best case, if there are no lamps at all, the initialization step can be skipped entirely. Here, only the queries are processed, which simplifies the time complexity to O, q, and the space complexity also to O, q. On the other hand, in the worst case, if every cell in the grid contains a lamp, then L equals n squared, and processing all queries results in a time complexity of O, n squared plus q, and a space complexity of O, n squared plus q. For average cases, where typical input sizes have L and q values much smaller than n squared, the complexity tends to remain closer to O, L plus q, 4 times n O, L plus n plus q, for space. Comparing this to a naive approach, where we would evaluate the illumination for each query by iterating over all lamps, the time complexity would balloon to O, L asterisk q, which is highly inefficient. The space complexity in the naive case would still be O, L plus q, but the time cost renders it impractical for large grids. The optimized approach described here is far more efficient than the naive method. By employing dictionaries to track illumination counts and a set to manage unique lamp positions, we reduce the time complexity to O, L plus Q. This is a significant improvement over the naive O, L asterisk Q. The space complexity, on the other hand, remains manageable at O, L plus N plus Q, as it efficiently leverages the limited number of rows, columns, and diagonals in the grid. Mathematically, the big O justification becomes clear. Initializing the lamp positions contributes an O, L cost, as each lamp requires constant time operations for set and dictionary updates. Processing the queries contributes an O, Q cost, as each query involves constant time checks and updates for a fixed 3x3 grid. Since these two steps are independent, their complexities add up, resulting in O, L plus Q, overall time complexity. Meanwhile, the space complexity is driven by the number of lamps, the grid size, and the queries, giving us O, L plus N plus Q. This balance of time and space efficiency makes the optimized approach well-suited for solving the grid illumination problem effectively. One of the most common issues when solving grid illumination problems is overlooking edge cases. For example, you might forget to handle scenarios where the grid is empty, there are no lamps, or queries fall outside the grid boundaries. It's crucial to validate all inputs and ensure your algorithm handles these gracefully. Another mistake is using an inefficient grid traversal method, such as directly iterating through all lamps for each query. This brute force approach can lead to a time complexity of O, N squared, or worse, which becomes impractical for larger grids. A more efficient approach involves using hash maps to track illuminated rows, columns, and diagonals. Without this, you risk performing redundant calculations that slow down your solution. Additionally, be mindful of diagonal calculations. Remember, the primary diagonal is represented by row col, while the secondary diagonal uses row plus col. Mixing these up can lead to incorrect results. Finally, when turning off lamps after a query, make sure to properly update the illumination status for affected rows, columns, and diagonals. If this step is missed or done incorrectly, your solution will produce errors. To excel in interviews, it's important to recognize patterns in grid problems, such as rows, columns, and diagonals. Efficient solutions often rely on tools like hash maps or sets to track these patterns. Interviewers are typically looking for your ability to optimize beyond brute force methods. For instance, using hash maps to track illuminated areas significantly reduces redundant computations and improves efficiency. It's also crucial to understand space-time trade-offs. While hash maps and sets help optimize time complexity, they require additional space. Be ready to discuss these trade-offs with your interviewer. Additionally, thorough testing is key. Interviewers may challenge your solution with edge cases or large inputs, so always validate your algorithm against such scenarios. If you want to practice related problems, try tackling LeetCode 212, Word Search 2, which also deals with grids, or LeetCode 37, the Sudoku solver. Problems like LeetCode 54, Spiral Matrix, and LeetCode 1284, Minimum Number of Flips to Convert Binary Matrix to Zero Matrix, are excellent for building a deeper understanding of grid-based logic. When considering alternative approaches, the brute force method is the simplest place to start. In this approach, you check the illumination for each query by iterating through all lamps. While it's straightforward, its high time complexity of O, N squared, or worse makes it unsuitable for large grids. A more efficient alternative is to use hash maps to track the illumination of rows, columns, and diagonals. This optimization reduces the time complexity to O, N plus Q, where N is the number of lamps and Q is the number of queries. However, it does require additional space. Another approach involves maintaining a grid where each cell directly tracks its illumination status. While this simplifies query checks, it requires O, N squared, space, making it less practical for large grids due to high memory usage. The key takeaway is to always understand the problem's constraints and explore optimizations that reduce redundant calculations. Balancing time complexity, space complexity, and solution accuracy is crucial for crafting an effective approach. Great job reaching the end of this walkthrough. We reviewed key strategies and concepts for solving grid illumination efficiently. Keep practicing grid-based problems to sharpen your skills. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!